So we're looking at this set of notes for today, the Laplace transforms of discontinuous functions. And what I'd like to do is I'd like to start us out with first a review. There we go. So first of all, what is, when can we define the Laplace transform, folks? We can do it for a piecewise continuous function. Of what order?
Nth order, right?
Nope. These aren't for this. When I say order here, I'm not talking about the order of the equation we're solving. This is some sort of restriction that we have to put on the function in order to. Exactly. We've got to say that it's of exponential order, which means it grows no faster at some point, from some point onwards, it grows no faster than an exponential function. Or put it, really what we mean is we can bound it by an exponential function, but the consequence is that it grows no faster than some exponential function. Okay? Then the Laplace transform exists, and how do we define the Laplace transform? It's the integral from 0 to infinity of e to the minus st f of t dt. Okay. What else can we say about the Laplace transform? It's got this really nice set of properties that we combine together to call them the linearity properties, so we say it's a linear transform. Okay, so absolutely you need to have these Laplace transform. I mean, I'll give you on the test, I will give you a formula sheet that has these, but I don't think you should have to look those up. I think you should have done enough of these problems and be familiar with this, that these, a number of these transforms are just readily available in your memory. But I will give them to you, but let's just remind ourselves of how these go. This is n factorial all over s to the n plus 1. That's how we transform polynomial functions. That's for n, a natural number, or 0. Okay. Technically, folks, it actually works for fractional powers as well, but I don't really want to get into that. That's another topic. And then we've got the Laplace transform of e to the at. We derived that. That was 1 over s minus a, and that works for, I should have said this here. This works for s greater than a. When does this work? This works for s greater than 0. Okay. So then the Laplace transform of the cosine of at, we said was s over s squared plus a squared, and that holds for s greater than 0. And for the sine, that is a over s squared plus a squared, and that holds again for s greater than 0. Okay. I don't really want to ask you problems that take forever to work through. I did put one challenging Laplace one on your exam review that involves the sort of integration by parts twice trick. But you should be aware of where these Laplace transforms come from, and you should be able to prove a number of, certainly if this were a 1 here, or maybe even a 2 there, or for anything e to the at, or any constant, you should be able to prove those Laplace transforms using the definition. So here's this example that we had before, where I did the integration by parts twice formula. We then get down to the point where we evaluate the limit. I want to talk about, now that we've got this new vocabulary, another way of resolving this limit. Okay? So normally what we had to do, right, was we did a review of the L'Hopital's rule. And we said, hey, if we go ahead and plug in this beta for t here into these expressions and beta gets large, well, the exponential will eventually pull it down. And we showed that with the L'Hopital's rule. But now we could actually say this better, because what do we know about t squared? T squared is of exponential order. Which means that it grows as fast as some exponential function or less. Okay? And so in this case, we can actually conclude that these limits will all go to infinity, or all go to 0, as beta goes to infinity. And so all we're left with is the lower limit that we're evaluating at 0. And in this case, we see, okay, everything that has a t proper as a polynomial in there goes to 0 as well. So the only thing we're left with is minus 2 over s cubed e to the minus s times 0, or just, excuse me, minus a minus, so that would be plus 2. So plus 2 over s cubed e to the minus s times 0, which is just 2 over s cubed. And already you can see how that sort of fits into this formula that we had up here for the Laplace transform for t squared. It would be 2 factorial over s cubed, and that's precisely what we get when we do the integration by parts, in this case twice on this.
Do you want a justification, like when we say that those terms go to 0 of like by growth rates or whatever? Because what that really is, we defined s as being greater than 0, so really that's 1 over e to the st, and so it's like a power of infinity, kind of. So, like, do you want a justification of this is because of growth rates or what?
I want, if you're doing this with the limits, I want either a statement, well, What I don't want is, I don't want you to jump from here to here with no comment. To go from here to here with no comment. So from this line to this line here. So
are the slash marks with the zeros adequate comment?
Let me add, since t is of exponential order. T squared is of exponential order. How about that?
And then, like, where you evaluate from 0 to beta, like, is that a super necessary substitution to make, or can we be like the limit as t goes to infinity without doing the, like, sticking a beta in there instead?
That I do want to see. I do want to see you write this part. The limit as beta, instead of putting an infinity up here. Yeah. Because it should be dealt with as a limit, and you can't use t because t is still a variable and it takes on the value 0 as well. So that's why you have to introduce this other variable beta. Yeah.
Okay.
Good questions. Good questions. Okay, so folks, here's an example of a inverse Laplace transform problem. So what did I do with this? I went ahead and first factored it and wrote it this way, into factored form. And then I went ahead and just, what did I do here? It looks like I did the partial fraction decomposition on this. Okay, so there's actually quite a bit of work between this line and this line. So between here and here, I did partial fraction decomposition on that. Once I do that, I then start trying to break things up to make it look like some of my basic elementary Laplace transforms. So usually it's helpful to factor out constants like I did here, here, and here. I just pulled out all the constants. If you want to do it all in one step, you're welcome to, but for showing this to you guys, I did it in 2 steps. I pulled out all the constants. And then this guy's ready to be inverted, so I left him alone. This guy's ready to be inverted, so I left him alone. But this one is going to come back. I can see already it's going to come back as some sort of sign. And in this case, my a here is the square root of 2. So I need, for sign, I need to have a square root of 2 up there. So I went ahead and put a square root of 2 in the numerator of that fraction right here. But then I had to compensate by dividing by the square root of 2 in the denominator of the fraction on the outside. So now we're ready to pull all this back into t space, and we get 1/3 e to the, watch it, minus t minus 1/3 cosine of the square root of 2t plus 4/3 radical 2 times the sine of the square root of 2t. Okay. So folks, I mean, there's, this would be kind of a challenging problem. Specifically doing the partial fraction decomposition of this would take you a little while, but I just wanted to show you how these often work out. Any questions on that? So this is, again, sort of just a review. I'm trying to, we're learning this at a pretty fast pace. So I just wanted to go backtrack and review a couple of these ideas. Thanks, Gilbert. Anyone else? Questions or comments? Yeah, if you're good, a thumbs up is always helpful if you know how to give those. That works. It works. Cheney, how you doing there? Good, good. Okay, great. All right. So we looked at this translation theorem last time, and I derived it for you. This is our first translation theorem, and it says if you already know how to do the Laplace transform of f of t, then when you multiply f of t in t space by e to the at, that shifts the Laplace transform in s space a units to the right, if we think of that as a being a real number. Okay, so multiplying, this isn't much of a mnemonic, but what we're saying is multiplying by e to the at in t space shifts the transform a units in s space. So let's do a couple of these working both ways. In my opinion, after you do a few of them, going forwards with the Laplace transform isn't too bad, but I think it's always a little bit tricky coming backwards with the inverse transform. Okay, so here we're asked to do the Laplace transform in letter A here. We did this one yesterday, but I want to go ahead and review it anyway. So we did the Laplace transform, or we know how to do the Laplace transform of t minus 1. What is the Laplace transform of t minus 1? So Laplace transform of t minus 1. All right, well, I'll do it. There it is. Right? What's the Laplace transform of 1? It's 1 over s. What's the Laplace transform of t? Well, it's t's power factorial, so 1 factorial all over s to t's power plus 1.
And you're using the fact that it's linear there to distribute it.
Yes, yeah, you're exactly right. So yeah, let's just comment on that. In fact, well, no, we won't change horses. So yeah, this is the Laplace transform of t minus the Laplace transform of 1, and we need that linearity property. Otherwise, we'd have to derive this one individually, which would be a pain. So this comes out to be 1 over s squared. When this thing gets hot, it doesn't copy quite as nicely. 1 over s squared minus 1 over s. Okay. So we know how to do the Laplace transform of t minus 1. So what is going to be the Laplace transform of e to the 2t times t minus 1? Well, what did we just write up here? We said multiplying by e to the at in t space shifts the transform a units in s space. So I'm just going to take my answer from before and I'm going to shift it 2 units in s space. By the way, I thought that this was kind of interesting. You should see 2 reasons why we ended up with 1 over s minus 2 there. There's 2 reasons why we ended up with 1 over s minus 2. The first one is what we just did about applying the shifting property. But if we had just sort of distributed this e to the 2t to both terms before we had done that, we would have had this as our transform. And so you can also see why 1 over s minus 2 showed up there. There's 2 ways of thinking about it. And that's nice to see the internal consistency of these rules. Okay, so let's have you guys try B. So have you guys tried... Oops, that's an inverse... sorry, folks, that shouldn't... Why is that an inverse transform? Never mind. Sorry, let's have you guys try C. I apologize. I'll do B here in a second, but sorry, I wanted to do the two straightforward transforms. So have you guys try C here.
Are you okay with us memorizing stuff, or do you want to see the integration that goes through that?
No, you can jump straight if you're comfortable. Oops, and I didn't write that right. If you're comfortable jumping straight to the answer, that's fine. I find and I would normally do that too, I think, but I find as far as explaining it to people, it's easier to say, hey, we know the Laplace transform of the cosine of 4t. We're going to take that answer everywhere we see an s. We're going to subtract 2. Oops, what should I have here, folks? You should be
plus 2.
plus 2. Yep, good.
So I was close. I just I added 2 to the 16 instead of adding it to the s. But
yeah, so that's important that it happens right inside of that function, right in place of the s. You're replacing s with s plus a.
I'm following now.
Or sorry, let me say that again. You're replacing s with s minus a. In this case, it was a plus 2. Okay, let's look at B here then. So it's a little bit harder to go backwards. Okay, we would have normally we recognize that this looks like the inverse transform of. So one way to look at it, it looks like the inverse transform of 1 over s to the 4th, which we know would be 1 over 6 times t cubed. Right? Because what's the Laplace transform of t cubed? Oh, that's ugly. The Laplace transform of t cubed would be 3 factorial over s to the 4th. And so we're missing that 3 factorial, so that's why we divide it by 1/6. Okay, so that's the inverse transform of 1 over s to the 4th. And so how would we go backwards for 1 over s minus 3 to the 4th? Well, we've shifted along s space 3 units to the right, so that would have been equivalent to multiplying this expression by e to the 3t back in t space. Now, I don't remember if we did letter D last time. I remember doing B with you guys. Did we do letter D last time, or did I skip it? Well, it doesn't matter. We're going to work it. Oh, does anyone know? Okay, I can't remember if we worked it or not, but we're going to work it now. So there's a couple different ways to do this. I'm going to do it one way here, and then I'm going to do it a different way in the next problem. So the first thing is I'm going to go ahead and start factoring this thing. And by the way, here it's not apparent. I don't think it's clear right off the bat that we're going to be using this translation theorem. Okay? I don't think it's clear right off the bat that we want to use that e to the minus or e to the at expression in our answer. But what do we try to do? We start trying to do our partial fraction decomposition. We start trying to break this thing up. So the first thing you do is you look and you say, hey, does this thing factor over the real numbers? And it doesn't because it's got a negative discriminant. The quadratic in the denominator has a negative discriminant. So it's not going to factor over the reals. So I'm going to try to complete the square sitting inside there. So let's do that. So completing the square sitting inside here gives me s squared plus 6s. And then if I were to complete the square on that, I would add 9 to complete the square. So outside of the parentheses, I'm going to subtract 9. So this gives me the inverse transform of 2s plus 5, and I'll just take an extra step on this, of s plus 3 quantity squared plus 25. Now, there are two ways to do this problem. I don't know if I'm doing it the long way or the short way, the hard way or the easy way. I don't know. But I'm going to go ahead and work it this way. I look upstairs and I look at what I've got before and I see, okay, I'm going to have to be using some sort of translation theorem because of that s plus 3 there, because I had to complete the square. So I need to, everywhere I see an s, have an s plus 3. Okay? So upstairs, I'm going to go ahead and next to the s, I'm going to put a plus 3. But if I do that, I've upset the balance of this equation somehow, right? I've now added 6 to my numerator. Everyone see that? I've added 6 to the numerator. So to compensate for that addition of 6, I've got to subtract 6 from outside of this. So what I'm left with is the inverse transform of 2 times s plus 3 minus 1 all over s plus 3 quantity squared plus 25. And like I said, if you see another way to do this, you're right, there is another way, and I'll use that technique in the next one. But I wanted to show you what you would do sometimes if you had, so here the issue is we had a factor of 2 sitting here. I put a plus 3 next to the s, so I didn't compensate by subtracting 3, I compensated by subtracting 6. Okay. So now I'll go ahead and use the linearity of the Laplace transform, and I'm going to write this as 2 inverse transform of s plus 3 all over s plus 3 squared plus 25 minus 1 over 5 times the inverse transform of 5 over s plus 3 quantity squared plus 25. And I did it again. Try as I might, I can never avoid doing s's and 5s. Okay. Anyone have any questions about that? This is a 5 here. So now's a good time. If you're feeling good, give me a thumbs up. If you're confused, I don't know if they don't have like an anti-thumbs up button, but sorry, thumbs down is what they call it.
Where did the 5 come from?
Mm-hmm. Yeah, great question, Gilbert. So I wanted, I looked for this expression right here. I was currently in the position to have, we had something like 1 over s plus 3 quantity squared plus 25. Now, ignoring the plus 3, this is looking like it's going to be a what inverse, a what Laplace transform. So this sort of looks like 1 over s squared plus 25. We'll worry about the plus 3 sitting inside there in a minute. But what is this the Laplace transform of?
Sine.
That's the sine, right?
I see.
But to be sine, I need to have what in the upstairs? I need to have a. So here, a squared is 25. So we know that a is 5. So I want to have a 5 up here. So I just go ahead and give myself a 5. But then to compensate, I multiply everything by 1/5.
Okay, that makes sense. Yeah.
Yeah, great questions. All right. Okay, so coming back now into T-land, we get 2 times, now here's the new issue, right? So we've come back with some of these trig functions before, but this time it's trig functions that have been shifted by 3 units, careful, to the left. So they're going to come back as 2e to the minus 3t times the cosine of 5t minus 1/5 e to the minus 3t times the sine of 5t, which, if you remember our spring equations, that's a typical answer from a spring equation. So that's why we're focusing on doing inverse transforms of this type. Anyone have any questions on that? Great, thank you. No questions. Okay, so now let's go ahead and do this one here. Just to give you one more bit of practice with this, because I find this decently tough. What I'm going to do in this one is I'm going to go ahead and use the linearity of the transform right away. And right away I'm going to write it as s over 2 divided by s squared plus, and here I'll start completing the square on this, 4s plus 4 plus 6 minus 4. Okay, that's for the first. And then for the second, we get the inverse transform of 5/3 all over s squared plus 4s plus 4 plus 6 minus 4. Okay. Folks, I don't require you to show a lot of work for these. You just got to get them right. And I've worked a few of them, and I know how much work I need to show to generally get them right. Okay. All right. So I can go ahead and take another step. I'll factor out that 1/2. And I've got the inverse transform of s over s plus 2 quantity squared plus 2 for the first piece. And then for the second piece, I'm going to do this. I'm going to write it out, and then I'll come back and add to it. So I've got my 5/3 that I pulled out. And then I'd have the inverse transform of, that would leave me with a 1 right here. I'm going to change that in a moment. S plus 2 quantity squared plus 2. And then sort of like what we saw before to Gelber's question, I notice that this second piece is going to come back as a sine again. And here a squared is 2, so that makes a the square root of 2. So I want to get a square root of 2 right there. So I go ahead and put a square root of 2 right there, and then I need to compensate by dividing by a square root of 2 outside. So now we're ready to pull everything back. Ooh, that's ugly. So now we're ready to pull everything back, and we get 1/2 e to the minus 2t cosine of the square root of 2t plus 5 radical 2 over 6 times the sine of the square root of 2t, where I rationalize that denominator as I did it.
Do you need to get a s plus 2 and then
folks, I need my e to the minus 2t here. Sine of the square root of 2t. Oh, shoot. Yeah, I'm sorry.
Yeah, for the cosine term, you have to have s plus 2 on top as well.
Yeah. Shoot. Yeah, why did I think I didn't have to do that?
You make the original s over 2 plus 4, so that when you take out the 1/2, like the factor of 1/2, you have an s plus 2 still there.
You can have s plus 2 minus 2 and split it into two different
Right.
fractions.
Folks, I'm sorry. I thought when I was thinking about this beforehand, I thought I could do it either way, and I really can't. I do need to. I'm sorry to change this on you. I do need to do this same problem the same way I did up above, where I do the adjustment first and then split it up. I'm sorry. For some reason, I thought I could do it. I could split it up and then still make the adjustment, which I could do. But if I split it up and then make the adjustment, I'll introduce one more sine term into the problem. Okay. So Christine, what I could do I think you were asking, what I could do is I could put a plus, I could put a plus 4 here. That's fine, but now I've unbalanced it, so I'd have to compensate by subtracting a 4 out here. So even though I would then divide out the 1/2, I'd still have the problem that eventually I'd have to break this up into its own Laplace transform. So I'm sorry about that, folks. I thought for some reason I could go that direction, and I should have run through that beforehand. So let's do this again. So we get the inverse transform of, and we can see that we're gonna, since we've already started factoring this, if you don't mind, I'll go ahead and just write this as s plus 2 quantity squared plus 2. And then, so what would I like? I'd like to have an s plus 2 up above here, but I'll need to compensate. I've upset the balance by adding 1 to this problem, so I'm going to compensate by subtracting 1. Do you have any questions about what I just did there? So I put the plus 2 right next to the s. So the way we look at saying what we just did was we just upset the balance by a 2 over 2, which is a positive 1. And so we compensate it right here by subtracting 1. Okay? And so then what do we have? We've got the breaking this up, factoring out the 1/2, we would have s plus 2 all over s plus 2 quantity squared plus 2. And then the minus 1 and the 5/3 is a 2/3 that I'll go ahead and factor out. And then we'll have the inverse transform of, in the denominator, we'd still have that s plus 2 squared plus 2. And so we factored out a 2/3, so I'd have a 1 there, but what I really want is a square root of 2. So let's just go ahead and give ourselves the square root of 2 there, and then compensate by dividing by the square root of 2 there. So now we're doing it a little more slowly, a little more, and we're doing it correctly. So it gives us 1/2 e to the minus 2t times the cosine of the square root of 2t plus rationalizing that would give us 2 radical 2. So radical 2 over 3, and then the e to the minus 2t sine of the square root of 2t. Folks, any questions where this e to the minus 2t in these two terms shows up from? Let me do that in a different color. Any question about where this e to the minus 2t came from? It came from the fact that it was a cosine curve shifted 2 units. Thanks, Gilbert. And this one came from the fact that we had a sine curve shifted 2 units. Okay. All right, so let's go ahead and practice solving a differential equation again. And we'll do everything together except for the partial fraction decomposition, which I went ahead and did already for this. So, solving this ODE, and I'm going to go kind of quickly through this part. Stop me if you have a question, though. That's s squared y sub s minus s y sub 0 minus y prime of 0 plus 4s y sub s minus 4y sub 0 plus 6 capital Y sub s is equal to 1 plus e to the minus t. Oops, sorry, not 1 plus e to the minus t. We got to do the transform of that, so it's 1 over s plus 1 over s plus 1. Just take a moment, make sure that makes sense. To be honest, it's that translating the differential equation usually isn't the hard part. Usually the hard part's doing some of the other work we've been doing. Okay. Well, in this case, so first of all, any questions on that, folks?
Yeah, what happened to the 4s y sub s, y of s?
This guy right here?
Yeah, because I see obviously all the y's of 0 are evaluated at 0, so they just go away, right?
Oh no, I haven't done anything on the right. This is both sides of the equation here, Edward.
Okay.
Yeah, so on the right-hand side of this equal sign, I did the Laplace transform of 1, which is 1 over s.
No, I got it now. Thank you.
All right. Okay. Okay, so in this case, as Edward was saying, this goes to 0, this goes to 0, this goes to 0. And so we're left with s squared plus 4s plus 6 y sub s is equal to 1 over s plus 1 over s plus 1. Okay. So you know the drill. What do we try to do? We try to solve for y sub s. We're well on our way. We get y sub s is equal to 1 over s times s squared plus 4s plus 6 plus 1 over s plus 1 times s squared plus 4s plus 6. Okay. Oops. Let's look at this second term here. You don't have to worry about jotting this. Don't jot this down. I just want to make sure we're all clear. For this second term, how would you go about doing the partial fraction decomposition? You would set it up this way. Right? And then you'd go ahead and you would do your partial fraction decomposition on this. Does everyone feel like if you're on a desert island with nothing better to do, you might as well do this by hand? You could work through it? You could get through that, figure out what A, B, and C are?
You'd have to be pretty bad for that to be the best thing to do, but I think I could manage.
All right. Okay, so notice, first of all, everyone notice you cannot use your shortcut on this one. How come? That's an irreducible polynomial. And the shortcut only works if everything's linear and non-repeated roots. Okay, so I went ahead and asked, I don't know who I asked. Maybe it was Wolfram Alpha. I asked somebody to do this for us. And when I did this, when I asked them, we got, for the first one, we got 1 over 6s plus negative s minus 4 all over 6 times s squared plus 4s plus 6. That's the partial fraction decomposition of that first fraction. And then I asked it to do the second one, and we got 1 over 3 times s plus 1 plus negative s minus 3 all over 3 times s squared plus 4s plus 6. So I'll give you a second to copy that. Folks, you'll certainly have a test question where you have to do your own partial fraction decomposition, but it won't be one this hard because this takes way too much time to do. So what I would do is I'd find a way to give you that baby step. Sometimes I give you, I go ahead and give you the partial fraction decomposition. I say, hey, if you're to this point in the test, do the decomposition this way, or something like that, just to save us some time. But you should be competent in computing all those coefficients if you had to. Okay, so notice that two of these are like terms and I can add them together. So if I added these two, well, let's go ahead and write out the two non-quadratic terms. So when I added the two quadratic terms together, what I ended up with was, this would be minus, that's minus s over 2 plus 5 over 3 s squared plus 4s plus 6. Which, we're now going to take this all backwards to t-space. So the first one, y sub t, the first one comes out as what? 1/6, right? When I do the inverse transform of 1 over 6s, that comes back as 1/6. Everyone okay with that?
Yes.
Okay. Great. Thanks, Ryan. Thank you, folks. Okay. And if you don't believe me, take the Laplace transform of 1/6, then what do you get? You get 1 over 6s. Okay. The second one comes back as 1/3 e to the minus t. Any questions on that? Thanks, folks. Now, this last one we did right on the previous page. So this last one comes back like this. Now, I don't know whether this procedure has saved us any time. If we wanted to do this without using Laplace transforms, what we'd probably do is we'd look at the characteristic equation of this, the left-hand side. We would solve the corresponding homogeneous equation, and then we would either use the method of undetermined coefficients or the method of variation of parameters to come up with a solution to come up with a particular solution, and then we would combine those two components together. Okay. You can kind of see, notice that this would be if you did either variation of parameters or method of undetermined coefficients. There's our homogeneous, or excuse me, there's our particular, and there's our homogeneous. Somebody asked last time, from the Laplace transform, you can't tell which part came from which. Why? Because we solved the IVP instead of solving the ODE. Okay. By the way, if you wanted to solve an ODE, it'd be a little bit trickier, but what could you do? You would write y of 0, you would just call y of 0 a, and you would call y of 0, or y prime of 0 b, and then you would repeat all the way through this Laplace transform procedure, but it would be a heck of a lot harder, I think, with A's and B's to simplify that and bring it backwards. You just have to trace those constants all the way through, and then you could come up with the general solution to the ODE. But they're sort of, these Laplace transforms seem better suited, I think, to solving IVPs than ODEs. Okay, are there any questions on this, folks? Thanks, Ryan. Any questions, folks? All right, I'm going to go ahead and keep moving. I want to look at another, actually, let's see here. We're 55 minutes in. We can take a break. Let's take 5 minutes, and then we'll jump back into things. Did we do this theorem last time, folks? I don't think we did. Okay.
I don't think so.
So I'm sorry, I just gave it to you as a theorem here, and I didn't explain it. So anyway, I'll get back to that, and maybe if we get some a chance down the road, I'll go ahead and derive this one for you. But it says that if you take a polynomial times, or specifically a power function times f of t, that you get -1 to the degree of that power times and then you multiply that by the nth derivative of your Laplace transform. By the way, this shows you how you could actually, this shows how lower order, or how, let's say it like this, this shows how you could end up with an ODE in S space. Because by doing this procedure, you could introduce derivatives into S space. Okay. And we'll look at an example of that maybe on the last day. So let's go ahead and actually apply that theorem on this one here. So we've got the Laplace transform of t sine of kt, and here I'm going to go ahead and rewrite this as, just to emphasize it, it's the Laplace transform of t to the first power times the sine of kt. So the above theorem says we're going to take -1 and we're going to raise it to that first power, and then we're going to multiply this by the nth derivative, so in this case the first derivative, of the Laplace transform of the sine of kt. So folks, be careful. Whenever you're taking a derivative, you've got to identify with respect to what. Okay? So I can't actually compute this until I evaluate that Laplace transform, but we know how to take the Laplace transform of the sine of kt. It's just k over s squared plus k squared. Don't let me go too fast. Stop me if you have any questions there. So at this point, what we've done is applied the theorem. Okay. So I'm now going to take the first derivative. Why the first derivative? Because this was t to the first power that we were multiplying to it. Sorry to make you seasick. This was the first power that we were multiplying to it. If this were t to the second power, this would be a positive one, and I'd be taking the second derivative of this expression. So, taking the first derivative of this expression gives me -1 times. So here I'm going to just do the old quotient rule. So here's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom function squared. And that minus 1 should be multiplied to the entire expression there. So let me be a little careful. So if we clean this up, we end up with a positive 2sk, or let me write 2ks, all over s squared plus k squared squared. So right here I did the quotient rule. Any questions on that, folks? I want to reiterate where this might be interesting. We're not going to do one of these problems today. They're a little too hard. Well, I don't know if they're too hard, but for right now we're not going to worry about it. If I had this ODE, t y prime of t plus y of t is equal to 0, you could see that when you do the Laplace transform on this, what's going to happen? Well, when you do the Laplace transform on the first part, you'd have y sub s. And when you do the Laplace transform on the second part, you know, normally you just have s y sub s minus y0. But we've got the t power here, and so that's going to introduce negative 1 to the 1, and then we'll take the derivative of this expression with respect to s. And so that's how you would take, notice that this is a nonlinear ODE. This would still be nonlinear, but it might now be solvable in a way that we couldn't do before. Okay. Oh no, this wouldn't be nonlinear. When you do the product rule, you'd have sitting inside this product rule here, you'd have s. Oh, it would be nonlinear still. S y prime of s, first derivative of the second plus the second y sub s times s. But anyway, that's how you could end up with a diffy q when you do the Laplace transform. Okay. Now, sometimes that helps you, sometimes that doesn't help you. This is actually how you find, for those of you who have heard of the Bessel function, this is one way to find some of the solutions to the Bessel function is by doing the Laplace transform. And then this is a better, when you do that, this is a better ODE to solve than the original. Okay. So let's go ahead and solve this diffy q. So this gives us, transforming this over, we would have, and I'm just going to do it in one step here, we'd have s squared x of s minus 1 plus 16 x of s is equal to s
minus 1s.
Great question. I think it's just minus 1 because what it was s squared x of s minus s times x of 0.
Yeah, cool.
So maybe I shouldn't have tried to do that in one step.
No, that's totally fine.
Yeah, but it was so silly to do. S squared x of s minus s times x0 minus x prime of s, or x prime of 0. All over, and then on the right-hand side we have all over s squared plus 16. So this gives us, on the left-hand side, s squared plus 16 x of s. This zeroes out, and that is a 1 that we'll add over to the other side. So we get s over s squared plus 16 plus 1. So the solving for x of s, we get x of s is s all over s squared plus 16 quantity squared plus 1 over s squared plus 16. And I think this is a pretty cooked up example I took from another book. It's pretty cooked up in that we did these two questions side by side. The previous question and this one. If I then go ahead and put a 1/2 right here. Oops, sorry, not 1/2. Let's see, 1/8 right here. Then I'd have upstairs. I'd put an 8, so I'd write it as 2 times 4 times s, all over s squared plus 16 squared plus 1 over s squared plus 16. So, folks, what did I do there? I wanted to get the number 8. Actually, I wanted to get the number 2 times 4 up there. So I went ahead and put it 2 times 4 there. And then I put divided by 8 right there to compensate. Why did I do that? Because in the problem above, I've learned that the Laplace transform of t, we learned in the problem above that the Laplace transform of t sine of kt would be this expression right here. And notice that I've just built an expression that looks like that right here. So I can do the inverse transform of that. So this is going to come back as 1/8 times t sine of 4t plus the sine of 4t. How did I know how to come backwards to this? It was from doing the part before it. I saw a question, Edward.
Yeah. So I thought maybe I figured it out on my own, but the plus 1 you had on the right hand side, that's for the positional argument, right? When you add the plus 1 to the right hand side.
So this was x prime of 0 was 1. And so I put a 1 there, so I've got a -1 right here that I then added over here.
Oh, okay. Oh, thank you.
Yep. Folks, any questions about this example?
I guess if we're just doing these on our homework, is that something we should probably look for kind of in a way, or we'll notice if we've just worked out one single?
Yeah, great question. Like, how would you know to do this trick? And I don't know if you would. I don't think I would have looked at something like this and known what to do immediately. What you could do is you could go ahead and rewrite this as s over s squared plus 16 times s squared plus 16. And then you could do partial fraction decomposition on that.
Okay.
And that would be a little bit of a pain, but you would eventually decompose it. And I think that would help you then in the process of bringing it back. And I'm not exactly sure how it would all work out, but I think then you could get there the same way.
Okay.
But this is a cooked up example. Yeah. In fact, that's what goes there. This is cute because I don't think you would know to do this. Somebody's done it for you. Okay. By the way, folks, this is not a problem. If I get any chance on the last day of class, I'd like to talk about this. This is a spring problem, right? Second order ODE. It's a spring.
Yes.
It's a spring problem, and it's got a forcing function on it, right? Now, I can put any forcing function that I want here, and we've learned how to deal with them using variation of parameters or method of undetermined coefficients, or in this case, we dealt with it using the Laplace transform. Okay? I did not stop to talk about this special case yet, and I hope to be able to do so again. Look at what our answer came out to be for this problem. Is there anything that's a little bit alarming for describing how this spring behaves?
added t on the sine 4t.
Yeah. So folks, a lot of times when we did these, maybe you got an answer of, sorry, this should be our x of t here. A lot of times we got an answer like x of t. So in this case, maybe, if we got, the cosine of 3t plus the sine of 3t, this is one of those idealized cases where the spring just continues, in its pattern forever. There's no dampening force, right? Or sometimes maybe what we would have seen is the overdamped case where we would have, or a damped case where we had like e to the minus 2t plus 3e to the minus 4t. A case like that. That was a overdamped system. Or we saw the critically damped system, x of t equals te to the 3t. There was a minus 3t. There was a critically damped system, right? And then a lot of the other cases, the most common cases look like this. E to the minus 2t sine of, I don't know, the square root of 3t plus 4e to the minus 2t cosine square root of 3t. And what was the, sine and cosine. What was this case? This was the case where you had an underdamped system and the graph looked like this, right? Which is how we expect most springs to behave, right? We expect it to behave like that, or the overdamped case, which would look like this, or the underdamped case, which maybe look like that, and the spring just stops, right? What's interesting about this case right here? So let's compare that to the, for example, the overdamped case, or sorry, the underdamped case. What happens as t goes to infinity to this system? X of t goes where as t gets large?
To 0.
To 0, and that's what we see in this graph, right? As t gets large, we expect the spring to eventually stop moving. This has a factor of t in it. Why did we end up with a factor of t in it? We ended up with a factor of t in it because our forcing function over here was similar to the root of the homogeneous equation. And the only way that could happen is if they have this has a imaginary component, or this has a spring, a period of 4t. Notice that this also has a period of 4t, and this is the phenomenon known as resonance. Have you guys heard of that?
Yes.
Yeah. So in some of your physics class, you might have heard of resonance, where if you start something vibrating at its natural frequency, rather than it being a case like this where the energy dissipates, if you vibrate it just so that it's vibrating at its natural frequency, you're actually going to keep inputting energy into the system. And the graph of this spring looks like this. And it's eventually going to shake itself to pieces. Okay. So that's the classic opera singer hitting a high note and shattering a wine glass. That's because the note that they're singing at forces this lattice structure of the wine glass to vibrate at its natural frequency and shakes it apart. We see resonance occurring whenever we have something like that show up in our solution to a harmonic system like this. That is resonance, and as time progresses, it's just going to shake itself apart, because this is going to tend towards infinity as t gets large, and no system can sustain that. So anyway, that was kind of a side topic.
Hey, Charles.
Yeah.
Should there be a factor of 1/4 on that sine of 4t term on the problem?
Ooh, good catch, Christine. Yes, exactly right. This should have been, so we would have needed to put a 1/4 here to get a 4 here, and so then that would have been 1/4. Good catch on that. Yes, thank you. Nice. Okay, so folks, if we get a chance, we'll maybe do some more questions about resonance later on, but I just wanted to show you that. Okay. So we're almost caught up to where we left off last time. And so now I want to look at, but this has served as sort of a review of everything, I think. So we left off last time talking about the step function. and the shifted step function. So remember that the shifted step function has a graph that looks like this. It's 0, and it's kind of up to you. It's up to authors to, what is it before 0? Is it 0 or is it just not defined before 0? But it's 0 up to A, and then it's 1 from A onward. That's your step function. Okay. Now, to be honest, you could pick any other height for that step function. You could come up with other step functions, but that's what we call our unit step function here, and that's the shifted unit step function there. Okay. So, by the way, I finished that example out by saying this was cute, and the reason why I thought it was cute is because, well, we could do that using using other techniques. But now finally we're going to start looking at our discontinuous functions and how do we do Laplace transforms with discontinuous functions in a meaningful way, and that is a huge advantage over using any of the other techniques. Because what we see is that these functions, when they get moved over into S space, are continuous. As long as your S is greater than some A value, it'll be continuous onwards. And that's a really nice property of a function. So the first thing I want to do is I want to do the Laplace transform of the step function. All right, so who wants to get it first? What do we return to when we try to do a Laplace transform of something we don't know how to work?
The definition.
So this is going to give us the integral from 0 to infinity of e to the minus st times the step function of t minus a dt. Well, the step function is a piecewise function, and how do you integrate piecewise functions? By breaking it up appropriately. So I'm going to break this integral up from 0 to a of e to the minus st times the step function of t minus a dt, plus the integral from a to infinity of e to the minus st times the step function of t minus a dt. Well, this just gives us 0 plus the integral from a to infinity of e to the minus st dt. What just happened, folks? How did I get that 0, first of all?
You just multiply it by the value of the step function for those given values.
Yeah, so what's the value of the step function when t is between 0 and a?
0.
The value of the step function is 0 for any choice between 0 and a. Does that make sense? Everyone okay with that? Okay. And then what's the value of the step function between a and infinity? It's 1. And that's how we just end up with this integral to evaluate right here. So we finish evaluating this. We get the limit as beta approaches infinity of minus 1 over s e to the minus st evaluated from a to infinity. And here, so in this case, there's no competition, right? There's no L'Hopital's rule.
Beta.
Ooh, good catch.
Well, because I asked about it earlier, and I was like, hey, you can't do that.
Good catch. And so we end up with minus 1 over s. Sorry, we end up with minus 1 over s. Well, so the first term goes to 0, and we get plus 1 over s e to the minus s a. Or put another way, we get 1 over s e to the minus a s. And that's the Laplace transform of our step function.
So when we say a to beta, is t what's going to beta, or is
Yes, because this is t equals a to t equals
Okay.
beta.
Okay.
And so the step we didn't write was you'd have the limit as beta is going to infinity of minus 1 over s e to the minus s beta plus 1 over s e to the minus sa. And then this goes to 0. And so this would be the step that I kind of skipped in there.
Games are kind of fun if you're a little bit masochistic.
Questions, folks? All right. So we looked at this function last time. We wrote this as a unit step function last time. Let's go ahead and find the Laplace transform of this function, which is discontinuous at 2 points on the real line. Okay. So last time we said that the step function for this, I'm going to write it out, you double check me, f of t is equal to t times the step function of t minus 3 times the step function of t minus 2. Oops, it's a minus 2. Plus 1 times the step function of t minus 3. So double check that all makes sense. Remember I told you to think about it in terms of flipping switches on and flipping switches off. So from 0 onwards, we flip on this switch. And then from 2 onwards, we add to it this switch, which brings our total y value down to -1. And then from 3 onwards, we also turn on that switch. And if you add from 3 onwards, that's going to be 2 minus 3 plus 1. So the output will be 0 from 3 onwards, which is what the graph shows it should be.
So the coefficients are basically what's happening vertically on the graph.
Yeah. Mm-hmm.
And then wherever time signature you're in, you subtract from basically at step -3 step t minus 2. It's going down from 2 to -1, which is 3.
Yeah.
It's going down 3, and it's at basically t equals 2. So you put t minus 2.
Yeah. So and the way I did this last time was I wrote it out this way. And you don't have to write this. But here I think of this one gets turned on from 0 to infinity. But at time t equals 2, this one gets turned on and the two cancel one another out. And then also I turn on this one at t equals 2 onwards. And so that's what's giving me that. There you can see the -1 there. I'm showing you that, Edward, because sometimes you've got to break these up into smaller pieces. But yeah, that's exactly right. And the way you can always test this is just plugging in some points. So what's f of 1, for instance? Well, f of 1 would be 2 times 1 minus 3 times 0 plus 1 times 0, because these other two step functions, we haven't reached the time value for which they'll be turned on for. But if we did f of, say, 2.5, then this function's still on. Now this function's turned on, but this function's still off. Because if t is 2.5, that one's on, but that one's still off. And then if we're at, say, t equals 4, we'd have 2 times 1 minus 3 times 1 plus 1 times 1, because they're all now turned on. And then that gives us a value of 0, whereas this one gave us a value of -1, and this one gave us a value of 2, which it should. Yeah, great, good observation on that. Okay, folks, so the question is how do we do the Laplace transform of this highly discontinuous function? Well, I shouldn't say highly, that's a loaded word in math. Let me just say of this discontinuous function. The Laplace transform of this is 2 times the Laplace transform of the step function, and here I'm going to just write t minus 0 just to emphasize what that shifting value is, minus 3 times the Laplace transform of the step function of t minus 2, plus 1 times the Laplace transform of the step function of t minus 3. So what does that give us? Well, we just saw in the previous example, how do we compute the Laplace transform of the step function? It's whatever your step is that a value there, or whatever whenever you turn it on. So this is going to be 2 times 1 over s, and I'm just going to emphasize this by writing e to the minus 0 times s, minus 3 times 1 over s, e to the minus 2 times s, plus 1 e to the, plus 1 times 1 over s, e to the minus 3 times s. When you clean this up a little bit, we end up with the function 2 minus 3e to the minus 2s plus e to the minus 3s all over s. And notice that this function is continuous and, more importantly, differentiable for all s greater than 0. What's
Would
that?
that be minus 3e to the positive 2s?
Let's check. So we said that the Laplace transform of, so notice when we had t minus a, it came out to minus as. So by our derivation, I think it should be negative. And that's a real pain. It's getting tricky to remember when you make things positive, when you make things negative. So that's certainly one that you would get on a formula sheet. So again, the rule is that the Laplace transform of the step function of t minus a is e to the minus as over s. So that's I mean, you could derive it the way we just did, but then that becomes a rule, and we had to apply it basically 3 times in this problem here. Yeah, so be careful with that. I would have expected that to be a positive as well, just kind of the way things usually work out when we do transformations, but it's not. It's a negative. So again, folks, what's really interesting about this is that we start off with a if this were a forcing function on a differential equation, it would be extremely difficult to handle the 3 different cases of our forcing function when we go to solve an IVP with this, or solve even harder an ODE with this. But when we take our forcing function and do the Laplace transform of it, it's a nice continuous differentiable function, which is really interesting. Now, what's going to be hard is, in my opinion, it's doing the Laplace transform of a step function and moving it into S space isn't too bad. I find it extremely tedious trying to map the result back into T space. And to be honest, I just go very slowly aligning things with the 2 theorems that I'm about to give you on the next page. Okay. So this function I called this the delaying function. Do we see why we call this the delaying function? So this is the function originally, and here it is after this is the delaying operation. And just to reiterate, how did we represent this? This second function here is let's call it g of t, and g of t is f of t minus b times the step function of t minus b. How does that work? Well, if I plug in a number smaller than b, the step function will output a 0, which is what I see I get until I hit b, time equals b. And then it starts giving me the graph of f of x, But what's happened to the graph of f of x? It's been shifted. So I also shifted the graph of f of x b units up here as well. Okay. So I'm not going to, I wanted to do the Laplace transform of this, but it takes a little while. It's a little bit tedious, and we're running out of time. So we'll put that on the back burner. We'll do that someday after the test. We'll come up with this. But if you do the Laplace transform of the delaying functions, there's two ways you can write that. Okay. So we've got these, number 15 here gives you the two versions of what's called the delaying theorem. So this says if you take the function f of t minus c and you multiply it by the step function, that's the same thing as taking e to the minus cs times your original function not being delayed. This I can't do, I mean, we'll derive these theorems next time, or not next time, but the next time we're actually doing work for the class. But to be honest, I have a hard time thinking about what all is happening here. And so I just sort of line things up and follow it piece by piece. Okay. So let's look at an example here. So actually, this statement actually is this tells us how to think about going backwards. So it says if you multiply f of s by e to the minus st, that delays or shifts f of t by c units. So that's at least one formulation, and that helps with thinking about this one here. But I don't have a good way really to think about this one here, and I don't have a good way to think about doing the Laplace transform, only about doing the inverse transform with it. But regardless, we're just going to follow these two formulas, and we're going to stick to the script. So let's look at the Laplace transform of this function here. Okay. So just following the script here, C is being played by the number 3 here. Okay. Now, which of these two formulas should I use for doing the Laplace transform based on what I'm looking at? Which of these two would be the easiest to apply?
Top one?
So the top one's got a t minus c inside the function, and I don't really have a t minus c in there. I could build one. I could put one there to let me use it.
Okay.
But I think the bottom one's a little bit more aligned with the theorem. So let's go ahead and use the second one. And so what do we end up with? We end up with e to the minus 3s times the Laplace transform of e to the t plus 3. There's a few different ways to think about this one, but to be honest, I'm just going to think about it this way. I'm going to rewrite this as the Laplace transform of the constant e to the 3 times e to the t. So you could also think about it by our translation theorem, our shifting theorem from before, but I'd rather just think of e to the 3 as a constant that I'm going to then pull out by linearity. And so we get e to the 3 times e to the minus 3s times 1 over s minus 1. Or in this case, we would have e to the 3 minus 3s all over s minus 1. Okay. So folks, I'm not really doing anything more than identifying the C, and then I'm identifying which of these two delaying theorems would be easiest to use, and then I just stick to the script of that. Okay. Now when we do the inverse transform, this little sentence that I gave you here might be helpful for thinking about doing the inverse transform. So let's look at number 18 here. I'm first going to rewrite f of s. I'm going to go ahead and break it up. So I get 1 over s e to the minus s minus 2 over s e to the minus 2s plus 2 over s e to the minus 3s minus 1 over s e to the minus 4s. Okay. So one way to look at this, and this is what I'm saying up here, is we could think of this as an f of s multiplied by an e to the... Oops, sorry, folks. This should be a minus cs in that sentence there. So multiplying f of s by e to the minus cs delays or shifts f of t by c units. So one way to look at this is e to the minus s times the Laplace transform of t minus 2 e to the minus 2s times the Laplace transform of t plus 2 over s times plus 2 e to the minus 3s times the Laplace transform of 3 minus 1 e to the minus 4s times the Laplace transform of t. Yeah, why did I put a 3 there? Everyone see how I did that? So then, really, this is the original function f of t, but we're going to delay it c units. How do you delay something c units? You shift it by c, but then you also have to introduce the step function, shifting it by c. So I'm going to end up with t minus 1 times the step function of t minus 1 minus 2 times t minus 2 times the step function of t minus 2 plus 2 times t minus 3 times the step function of t minus 3 minus 1 times t minus 4 times the step function of t minus 4. This is tough stuff, folks. I find this this is kind of maxing me out, I think. I haven't done it enough to be comfortable with it. Where we're using this this version, so we saw this right here. That's what we saw. We saw those little pieces. So look what I got a lot of marks on here. Let me clean some of them up. So I saw this expression down here. I saw an expression like that right there, right? So if I want to go backwards this way, I shift both f and the step function, whatever the value of c is. Okay. Okay. I think that's a good place to stop. What this means is that I did not get to doing the applications specifically where we have spring problems with discontinuous forcing functions. So those will not appear on the next exam, even though they're on the exam review. So I can go to the exam review right now and show you what you do not need to worry about on the exam review. Okay. But everything up to that, including using these step functions, is going to be on the next exam. Okay. So let's just pull up that exam review. So looking at the exam review, you do not need to do number 32. So for the exam review, you do not need to do number 32, nor 31, nor 27b. Those all involve doing Laplace differential equations with those Laplace transform or with those unit step functions, and I just want to I don't want to rush that on you. Okay. But what is fair game is using these step functions and doing just the Laplace transform of the step function or the inverse Laplace transform of something that has a step function in it, meaning an e to the minus st in it, or e to the minus e to the minus as in it, bringing it back as a step function. Okay? So for example, let's just look at one of these. Let's see here. Let's look at this one right here. Okay. So what does this look like? This looks like the Laplace transform of t to the fifth, except we're multiplying it by e to the minus 3s. So I'm looking at number 19 here. This looks like e to the minus 3s times t to the fifth. Okay. So if and to be honest, I don't have this memorized. I go back and I look at these delaying theorems. And I look at this one right here. So I've got, I had e to the minus 3s times the Laplace transform of t to the fifth. Then I'm going to bring it back by shifting inside of both of those by whatever 3 is, and by whatever c is. And so in this case, c is a minus 3. Oh, so no, c is 3. Careful, watch lining that up. There's a negative sign here and a negative sign here, and that's easy to make a mistake with. So c is equal to 3. And so when I go to answer this question, we're going to say that the inverse transform of this is the t to the fifth function, but it's shifted 3 units to the right, times the step function shifted 3 units to the right. And so that's what we get for, well, I don't know which option that is, up to the fifth power. And so that makes it look like it's choice D there. Okay. So be careful with using those delaying theorems. I find them a little bit tedious to work with, but you'll get some practice. Okay. So folks, that's all the content for exam 3. Just so you know, for the final, we're just going to do another day and a half or 2 days of Laplace transforms, and then the final will be a cumulative exam, and I'll be getting out a review for you as soon as I can. Any questions?
Will the final be a take-home also?
What would you guys like?
I'm very slow, so I would like a couple of days.
Okay.
I promise not to procrastinate.
Okay. Yeah, just know you gotta. I know you guys have a lot of other final stuff going, so sometimes it's nice to just have being told that you just have a one short window to do it in, as opposed to a day or two to work on it. Is anyone? If you object to that, just shoot me an email. Well, actually, we can do this right now. If you object to that, raise your hand, because you guys shouldn't be able to see if the hand's raised, right?
So the two options you're offering are what?
To do it in a synchronous fashion, where I say, okay, our final is supposed to be on the Thursday of finals week at 2:30 p.m.
Okay.
So that's
Would it be like from 2 to 5 again that it's available?
Yeah. Or to just say on Thursday I give it to you and you have to get it in by, say, Saturday or Sunday.
Okay.
Well, our other finals are going to be done by that point, right? So we could work on it Saturday and Sunday then?
Well, it depends. I think Monday is also a finals day. I think Monday the 11th is also finals day.
Yeah, Monday the 11th is the last day of class.
Well,
For,
piss on Ocam.
So, folks, I can't. So, you guys have well, it's recorded. I'm not going to go back. Let me stop recording now.
Do you have to edit out all my cuss words too?
No, I usually let those slide.